Hello and welcome. This is Scalars and Vectors Part 1. In physics, we need quantities. And there are basically two types of quantities. These are scalars and vectors. Let's write them down. Scalars and vectors. A scalar is just a fancy word for a number. So scalars are numbers. Okay, the room is 72 degrees Fahrenheit. That's a number. Okay, this pencil is 10 centimeters long. Another number. So it's just a number. What about a vector? Now, some quantities are more complex. Like if I say, okay, I live on the third floor in the apartment building, that's fine, you know, a number is enough. But what about if you want to define a location, right? What part of town do you live? Or what are the street names? Suddenly we move from a one-dimensional description to a two-dimensional description, right? I mean, the number of stories in a building is quite one-dimensional, right? Let's call this, as you go higher, the numbers go higher. But what about a location? Let's say this is Houston. All right, and you can be here or there or here. Now we have the north-south streets and we have the east-west streets, right? So you will need two numbers, you know, the 19th Street and then north-south direction, and 20th Street in the east-west direction, for instance. So when you go to 2D, D stands for dimension. All right, so that's only to locate a point on a plane, okay? So a position, in other words. So we could be talking about a position or location. How about points which are in motion? Let's say you're walking or you're in your car, you're driving, right? So you speed up, you slow down, you don't only change location, but the way you are present at each location at each time changes, right? The motion changes. So you need to be able to describe motion. You know, how fast are you moving? In which direction are you moving? Or this could be, okay, we talked about the room, temperature in a room. Okay, the temperature may not be the same everywhere, so you have a variation, you know. It's a scalar thing though. For each point in the room, you may have a number that describes the temperature in that room. But what if you suddenly open the windows, all right, and then there's an airflow, all right? So you don't only have the temperature, but now you have the air moving in one direction, all right? How fast is it moving, and in what direction is it moving? So that type of physical quantities are numbers plus direction, okay? So that's what a vector is. A vector is a scalar, a number, with a direction. All right? So if you are in 2D space, such as, you know, the surface, you're here. If I want to use the vector to find the position, I may pick a corner and draw an arrow starting from that corner, such as this one or this one. So if I'm given these arrows now, I know two things. first of all, I know how far I am from that corner, right, which is this corner here, and I also know in what direction from that corner that arrow is pointing at. Okay, so two numbers, two information bits. One of them is the length of the vector, which corresponds to that scalar we're talking about, and the arrow itself gives me a direction, right? So the two components of what we call a vector, when we use the vector as a tool for finding the position. All right. So in general, this could be in 3D as well. Let's say you're in a 3D room. I'm gonna try to draw a cube-like thing here, which describes the room, and there are points in the room. Let's say your TV set is over here and the kitchen is back there, and then you have something on the floor. Okay, so what if I pick this corner and then draw all my arrows from that corner? This is where your TV set is, this is where your refrigerator is, and here's something on the floor, right? So these three arrows uniquely describe these 3 points, these 3 objects in your living room or your kitchen or whatever, right? So a vector, again, this is what we call a vector, an arrow. We use it again to describe the location of an object in our space, but now we have 3 dimensions, so 3D. Okay, the dimension is 3 in this example. What about 1D? All right, if you're moving along a line, or if you're going up and down an elevator, remember the building here? Well, that's a one-dimensional motion, right? At a given time, you're either on the first floor or the second floor or the third floor. So you just draw your arrows starting from maybe the ground floor. Let's say you're on the second floor like this, then this arrow points up. If there's a basement, maybe the arrow points downward. That's where you are, okay? If you're on the 5th floor, then your arrow points up. So if you have a 1D problem, you know, the arrows are either pointing this way or the opposite direction. All right, call them plus or minus, positive or negative directions. All right, a positive direction or a negative direction. In 2 dimensions, you're talking about now angles. All right, maybe you're measuring this angle from this side here, and then you have a wider angle here to describe the second vector. In 3D, the angles are getting complicated. You know, from which side, you know, am I going to measure this angle? Will it be the line that is formed by this wall and the floor, or the other floor? Okay, you have to decide. You have to think harder for 3D. And what about higher dimensions? Well, we can't visualize them, but mathematically we can write them down. That's not something we're going to be interested in this class, but basically 1, 2, and 3-dimensional motion we'll be working on. All right. So a vector is again simply an object with a direction and a number. Okay. So let's just stick to 2 dimensions. In 2 dimensions, let's say we have this arrow, just like this monitor here, or you're on your paper, right? Draw an arrow, and that is your vector. Give it a name, A. This is your vector A, and put an arrow on top of it, like this, a small arrow. That means a vector, okay? When you look at a book, sometimes you won't see the little arrow on the top. Instead, you'll see bold face, okay, bold characters. That also means a vector, okay? Sometimes both bold and also an additional little arrow on the top means a vector. Now, obviously, this vector has a length. Okay, so you start from this tail to tip. You take a ruler, put a ruler here. Oops. And then measure how long this arrow is. A hypothetical ruler, right? Length. We're talking about the length of the arrow. That is our scalar that goes with the vector, okay? And that length has a name. We call it the magnitude. Magnitude of a vector, okay? All vectors have positive magnitudes. This will always be a positive number. Always a positive number. So please do not confuse this with the negative values you may have. Going back to the 1D example, you have the floors above the ground floor, which are positive numbers 1, 2, 3, 4, and then below the ground level you have basement. You know, you can call them -1, -2 if you like. All right. Yeah, but those negative numbers do not go into the magnitude. What you do then, you just flip the direction of the vector. Okay, so you either have a vector pointing up or pointing down, or if you're talking about a one-dimensional setting, which is a horizontal line. All right, here you have a horizontal line. Now this line could be from your house to the grocery store, right? Now this is a point somewhere in the middle. Let's say my arrows will start from that point. So any point to the right or any point to the left could be described by these two vectors, vector A and B. Now one of them is pointing to the right, one of them is pointing to the left, and if you wish you can call this direction to the right a positive direction and a negative direction. But if you measure the length of these arrows, you'll always get positive numbers. Okay, so magnitude is always a positive number, but you may flip the direction. Okay, so the direction and the magnitude, which is the length. If you use this representation of arrows, a magnitude corresponds to simply the length of a vector. Now, if you have two arrows, okay, let me scroll this. If you have two arrows, they point in the same direction, and the lengths are the same, okay? Now, we call these two vectors to be equal to each other, A and B. Now, what physical quantity may they correspond to? It could be anything. It could be position, or it could be something that has to do with motion, which I'm going to talk about in a little bit. But as long as they point in the same direction and they have the same length, they are the same vectors, okay? Now, this is not always true, but for our purposes, which is just a two-dimensional surface on the paper or on your computer screen where things are flat, okay? These two are the same. You're pretty much taking a vector and you're moving it. See, when I move like this, the length obviously remains the same. I'm not changing the direction, I'm just moving it. So at a given time, this represents a line, all right, a line like this. At a later time, when I'm moving it, now it represents another line. But these two lines are parallel, okay? Parallel. So I'm doing nothing but parallel transporting a vector. So this line here and this line are parallel. Parallel. So going from here to there, basically I just parallel transported. Okay, and if I'm on a flat surface, I end up with the same vector. So here A will be equal to B. But that's not always the case. If the surface is flat, it is the case, but what if the surface is not flat? All right? Now, what could be a two-dimensional surface? A surface is two-dimensional, but not flat. Well, the surface, if you think about the globe, a ball, right? Earth, for instance. I talked about Houston map, but it's not really flat, right? If you think about it, Earth has a curvature. So let this be Earth. All right, a sphere, which has the line here, equatorial line. All right. So if you think about the Earth, Houston is somewhere here, but think about a point on the equator. All right, in Ecuador, you have a point here. In Africa, you also have another point, right? Maybe here. Now let's start with a vector which points in the direction of north. Here's the North Pole. So my vector, if you think about it, this dotted line is actually a curve, right? A meridian, if you think about it. Now this points this way. That's my vector A. Now the rule for parallel transport is you don't change the direction, all right? And the length doesn't change. So you start from equator and you keep going north. Keep going north. Keep going north. You're here. You're still pointing at north. Keep going north. And then when you come to north, all right, you end up with a direction, let's say, like this. So what have you done? You've just parallel transported that vector. You started at a point on the equator. You kept moving north. And you ended up with that vector over here. But why you didn't have to go to north? You could just move in any direction. As long as you're not changing the direction of the vector, you could move it around, right? So what if you move along the equatorial line? Let's say you move from here to there, but you still want to point at north. You keep moving. It's also called a parallel, right? The largest parallel is the equatorial line. You move all the way to Africa, and now your vector now starts at a point somewhere in Central Africa, but you're still pointing to the north. The vector, the arrow, points to the north. And then from Africa, you move your vector along the meridian towards the North Pole. Now you're here. And then when you arrive North Pole, you end up with a totally different vector. Okay, the two vectors are pointing at different directions. So this doesn't hold on a curved surface. All right. In order to call A and B the same, the surface has to be flat. Just keep that in mind. So what can we use vectors for? Obviously, we could use them for showing the location of an object. All right. So let's stick to flat surfaces and 2 dimensions. So this is our paper. All right. A paper. You turn it like this, and then you want to trace the motion of an ant. Let's say you have an ant. Here you have an ant. And the ant will move from one side to the other. Okay, so the ant will end up here. And I'm watching the motion of the ant and trying to come up with some vectors to describe its location and motion in a sense. Okay, so the ant starts its voyage from this point here. Let's call this point 1, P1, and ends up at P2. Right? We can call them initial and final positions. Initial position and final position. Okay, letters I and F. Let's say I'm using vectors to describe the position, so I need a point to place my vectors, right? So the tail of the vector, let's say, will be from this corner of the paper. So I'm just going to draw an arrow like this. Okay, that's my initial position. And for the final position, I will need a different vector. The magnitude has changed and the direction has changed as well. So the second arrow will be describing the final position. All right. So let's call these position vectors. Let's use the letter R. R. Okay, so R stands for position vector, with an arrow on the top. And I'm initially here, so I'm going to call it Ri, the index here. All right, Ri. And for this one, I will use the letter F. So here's the vector Rf, the final position. Well, what about the points in between, right? I mean, the ant didn't jump, it actually followed the path. So this is the actual path of the ant, the path. And maybe I'm keeping a record of where the ant is, you know, every 10th of a second or something, or every second, depending on how fast, you know, the bug is moving. So maybe these points are here at equal time intervals. Okay, these points here represent the position of the object at each time interval. So this could be at time, let's say 0.5 seconds, and here 0.8 seconds. All right. Here 0.2 seconds, etc. Let's use the letter T for time, huh? So this is T. So if you just use dots to show where the object is, you call it a motion diagram, all right? And just by looking at the way these dots are spread, you can tell about the motion. Like in this case, they're pretty much equally spaced, right? If your dots are equally spaced, you can say, okay, the object had a steady velocity or speed, let's say, for now. Okay, didn't speed up or slow down, so they're equally spaced. But what if someone just gives you another example where the motion is 1D, but then you have dots spread like this? Let's say the car is moving to the right. We know that. All right, the motion is to the right, but the separation between the dots are increasing. All right. Since you know that the time intervals were the same, but the distances are getting bigger and bigger, you can say the car is speeding up. All right. And if this car was moving to the left, then you would say it was slowing down. Okay, so these are called motion diagrams. A motion diagram is not really a vector, it's just dots. Okay, so objects become like dots when you draw them. Okay, it could be any size object, it's flying in the room. You know, if we're ignoring things like rotations, all right, you can just pick a point on the object, just focus on that point, how it's moving. Or if you're thinking about the motions of planets and stars in the vastness of space, these are really small, right? It's almost as if you're squeezing all that volume into a dot, and then you're just tracing that dot in space. All right, so dots will be enough, at least for this part of our course, when you're ignoring things like rotations, more complex behavior. A motion diagram is pretty much a series of dots. Okay, now going back to vectors. Okay, so we have now the initial position vector Ri and the final position vector Rf. These vectors are pointing at those points where the object is at a given time, and the vectors have to start from the same point that you picked. It's totally up to you, okay? You can pick anywhere you like. I just picked that corner in that, this was my sheet of paper. I picked that corner, right? Now that has a name. We call it an origin. That point is called the origin. That's where your arrows are lined up. The tails of the arrows are there. Now, once you have your two position vectors, what can you do with these? Since the choice of the origin was up to you, okay, someone else watching maybe pick a different point on that line and pick different, end up with different position vectors. Example, let's say this is the path of the object and you picked here, right? So this was your initial and final position vectors, Ri and Rf, but maybe your friend picked a different origin, and in that point of, from that point of view, the vectors Ri and Rf look like these. Obviously, these are different from yours. Let's call it Ri prime and Rf prime. Now, are those measurements not correct? No, they're both fine. The measurements are different, but they correspond to the same unique activity, motion of the object. So when you do physics, when you describe events, you should be able to agree on what's happening there, independent of your choice of origin. So one origin was here, or one, another origin was there. There could be an infinitely many choices for origins, but one thing that doesn't change is the object moved from point A to point B, or point P1 to point P2, which means the position vector itself is not enough. Okay, we have to work with a vector that both observers could agree on, right? And that will be called the displacement vector, not the position vector, but the displacement vector. So let's talk about the displacement vector now. Displacement vector. Now this vector has to start from the initial location itself, which was this. It was P1 or Pi, right? Initial point versus final point. It has to start from the initial point and has to point at the final point. Okay, this is what we call the displacement vector. Now it doesn't matter from which observation point you're looking at it, because P1 and P2, or point initial and point final, correspond to the initial and final points, but the length between, the distance between those 2 points is the same, right? And since the motion was along the path, the motion was in this direction, our displacement vector has to point from I to point F, point P1 to point P2. So that vector is unique, all right? Displacement vector. Now, what are we going to call it? Okay, what are we going to call it? What symbol are we going to use? Now, the symbol is Greek delta, the Greek letter delta, and we put an R next to it. Okay, this is called the displacement vector. Now, why do we need two symbols? Why cannot you just say B, A, something else? Well, the convention is, whenever in physics you're talking about differences, okay, difference means final minus initial, you use the Greek letter delta. So delta in physics stands for final minus initial. All right. Now, what does this have to do with our displacement vector? All right. I mean, we know that we're going from point I to point F, but what is this minus sign? Okay, subtraction. It's an algebraic operation. How does it work with vectors? All right. So, in order to understand that, we have to know more about vectors. Now, what we're using so far is a graphical representation of vectors in the form of arrows. So we need to be able to understand how we do basic mathematical operations like addition or subtraction and later multiplication. All right. So if we establish those rules, starting with the addition of these arrows, we will understand why a displacement vector is actually a subtraction of two vectors. All right? So let's go back to the basic picture here of an arrow in two-dimensional space, a vector A, given A, and given another vector B. Okay, different length, different magnitude, also different direction. How do we add them? Okay, so addition of vectors. How do we add them? So the rule is, since you can move these around and you still have the same vector, remember, parallel transport, you move a vector without changing the direction, it is still the same vector. You take one of the vectors, doesn't matter which, you move it and bring it close to the other vector. For instance, let's say we move B. Okay, I'm going to move B up here and I'm going to bring it right here. Okay, I just moved B without changing the direction. I moved it up a little bit so that the tail of the starting point of the arrow, vector B, is now the same point as the tip of A. Okay, the tip of one of the vectors is where the tail of the other vector is. So if I have these vectors lined up like this, I could start from the tail of the first vector and I could draw an arrow to the tip of the second vector. So I could start from the tail of the first vector and draw an arrow to the tip of the second vector. Okay, tail to tip. And that's what I'm going to call the sum of A and B. So this is an addition rule, okay? This is how to add these two vectors. The vector in green, the arrow in green, becomes this sum, A plus B. Just the definition, okay? Just the definition. Or the graphical representation of adding vectors. But the rule is they have to be lined up like this. So if you don't do that alignment, For instance, let's say I moved B. Let's just draw A here. But I'm moving B and just putting it over here. Okay, imagine this is still B, and it is B. But I joined them from this point here. Now both of the vectors have the same starting point. The tails are matching, all right? Can you move the B like this? Yeah, you can move, but if you try to join these two with an arrow, okay, this is not A plus B. I mean, you can put an arrow if you like, okay? This is not A plus B, okay? In order for this method to work, you have to go from the tail of the first vector to the tip of the second vector, and the two vectors have to be aligned like this, so that the tail of the second vector has to be where the tip of the first vector. Now, could I move A instead of moving B? Yes, I can. So let's keep B where it is, but let's take A and bring it over here. So this is my A, this was B, right? And now I'm joining the tail of B to the tip of A. Okay, and according to my definition, this is B plus A. All right, now if you compare B plus A to A plus B, you see that they have the same length and they point in the same direction. Maybe my drawing doesn't really reflect it well because of my bad drawing skills, but these two are the same. So A plus B is equal to B plus A. So the order of this operation doesn't matter. Okay, you can change the order, you can commute them, right? The order doesn't matter, but that's how you add two vectors. What if you have more than two vectors? What if you have more than two? Okay. Let's say you have three vectors, A, B, and C, and you want to find this expression here, A plus B plus C. What do? Well, you start moving them, all right? So A is here, keep A where it is, but bring B close to A such that it starts from the tip of A. Now this is your B. Okay, you parallel transported B to here, and then you do the same thing for C. Now you move C over here. That's C, all right? You didn't change the direction, still the same vector. But now you have this alignment from tail to tip, and then tail to tip, tail to tip. What do? You start from the tail of the first vector and draw an arrow to the tip of the last vector. So this is now equal to A plus B plus C. And you could do this in any order. That wouldn't make any difference. You could add C first, let's say. This will give you C. And then B. You would still get the same vector. Okay, that is A plus C plus B. But that's the same as this one on the left. It's pointing the same direction and has the same length. Okay, so you can add as many as you like this. Now what if this happens? Let's say you have multiple vectors and you line them up. The only rule you're following is tail to tip rule, okay? You don't have two vectors that look like this. That wouldn't be tail to tip. And you suddenly realize that you come back to the same point. Okay, can this happen? Yes. I mean, you start from your home, you go to the grocery store, and then you go to, your friend, and from your friend you go to the movie theater, and from the movie theater back to your house. All right? So you may have a loop. If that is the case, let's call these vectors A, B, C. How many do we have? Let's see, you have A, B, C, D, E, and F, right? Okay, now at this point, if the last vector here was not present there, okay, if it wasn't present, I could say that this vector, which I would obtain by joining the tail of A to the tip of F as my sum, A plus B plus C plus D plus E plus F, right? But now I have an additional vector which goes from the tip of F back to the tail of A. So imagine this vector in white getting smaller and smaller and smaller until it becomes 0, right? So this vector in white is getting smaller and smaller because now I have another vector which I can call G, right? So what happened then? A plus B plus C plus D plus E plus F plus G. I'm back to where A is. The resulting vector would be the sum of all this, but it has a 0 length, right? So I call it a 0 vector. 0. 0 vector is a vector of length 0. It doesn't point in any direction, right? I mean, I could do it with just two vectors too, right? You go to grocery store and you come back straight home. So A and B, but you come back to where you started. So A plus B is 0. All right? So what does it tell me? Now just look at this equation. Forget about the arrows. Just look at A plus B equals 0. Okay, think of these as algebraic variables. And whenever you have equations, you can move things around in the equation, right? Like you add or subtract the same thing from left and right hand sides, and nothing will change. Okay, so that's how you solve equations. Like what if I subtract A from both sides? If I subtract A from both sides, I will only have B left on the left hand side, and 0 minus A will give me negative A. Alright? So now it looks like I've discovered a new rule. If I just put a negative sign in front of a vector, I'm pretty much flipping the direction, changing the direction by 180 degrees, right? Look at A and B. They're pointing in exact opposite directions. Their lengths are the same though. Magnitudes are the same. Magnitudes are the same, but opposite direction. Opposite direction. So in a vector language, you just put a negative sign in front of a vector. You're talking about a vector has the same magnitude but points the opposite way. Now there is this notation for magnitude. You just put bars around the vector, bars, 2 bars like this. This means magnitude of A. Magnitude of A. Sometimes you will just drop the arrow. It also means the same thing, okay? A shorthand. If you just write A without the little arrow on the top, you're talking about the length of A positive number, remember? So this is magnitude. So if you go back to the equation you ended up with here, the magnitude of B is equal to the magnitude of A. But if you write them as vectors, you have to include the negative sign because they're pointing in opposite directions. So why is this important? By using this rule, you can come up with subtraction methods. Okay, you don't need a new rule to subtract 2 vectors. The only rule you have is addition of 2 vectors. But now you know what happens to a vector if you put a negative sign in front of it. It just flips the direction. So if you want to find A minus B, right, these vectors here, this was, let's go back to A and B. Okay, the 2 vectors we started with, these 2, A and B. If I want to find what A minus B is, I don't need a new rule. I just need to write A minus B as A minus B as A plus negative B. Alright, same thing. Algebraically, these 2 are the same. And I know how to add vectors, so that's what I do. So let's write A again. Let's draw A. This was A. And this was B after parallel transporting it close to A. But I want to find A minus B. So what do? I put a negative sign in front of B, which gives me this vector. Now it's pointing in the opposite direction, but the lengths are the same, okay? Whatever length you measure here is the same as this. These 2 are equal length. So the vector on the left is negative B, all right? Negative B. And A plus negative B, I apply the rule I had. I start from the tail of the first vector and I go to the tip of the second vector. So here. All right. So this is now A minus B. All right. So that's how you subtract 2 vectors. Now let's try this. Since we are allowed to move these vectors in a parallel fashion and they're still the same vector, I'm going to try this now. I'm going to move B. I'm going to move B and bring here. Bring it right here. It is B. Right? I parallel transported B from here to there. Now both A and B start at the same point. All right? Okay, now what about A minus B? It is a vector. Can I parallel transport it? Yes. I'm going to parallel transport it over here now. I'm going to move it. It's still A minus B, right? A minus B. Now that's an interesting picture. Okay, so if you saw what happens here, you can just start with 2 vectors. A. Okay, that's not a very good A. A and B. In order to find A minus B, you just draw this vector here. That is your A minus B. Now we have this already. If you remember half an hour ago or so, I talked about the displacement vector. Remember? Ri and Rf. Now see how both Ri and Rf start at the same point, the origin. Whether it's O1 or O2, doesn't matter. I have an origin, both position vectors start at the same point. But now, this displacement vector, which points from point I to point F, is nothing but Rf minus Ri, based on this rule we just discovered, right? So let's write it here. Delta R is Rf minus Ri. All right, so that is your displacement vector. And every time you see the letter delta in physics, that will be every time or 99% of the time, it'll mean a difference. And that difference is, by convention, final minus initial. All right? So that's delta R. What else can you subtract? We talked about time values, right? Like, remember, going back to that ant, these points correspond to equal time intervals. You know, the variable t was changing. So why don't I call this point here ti, and this point corresponds to tf, a point in time. Now, time always increases, right? You never go back in time. So time has only one direction, in a sense. So if I subtract t initial from t final, I get delta t, which is always positive. Tf minus ti. We're going to call the time interval. We're going to call this the time interval. Okay, so when the object is at point I, you're looking at your watch, stopwatch, it says 1.5 seconds. All right, you have a chronometer or something. And then you look at it again. When the object is at point F, that's your TF. The difference between the two is your time interval. Now, most of the time, TI can be chosen as 0. You know, you start your stopwatch when you start running, and then you push the button again when you want to find your TF. So it's very common practice to take TI equal to 0. You don't have to, but it's common. Common practice, okay? Then you don't have to call TF. You can just call T. In that case, instead of delta T, you only have the variable T. So drop the I's and F's, pretty much. Drop the letter F, okay? But for now, let's keep it. So delta T is T final minus T initial. What am I going to do with that delta T? Well, I'm going to divide delta R by this delta T. And I'm going to call this the average velocity. Okay, average, which is also a vector. Okay, average velocity vector, just the definition. All right, now going back to this picture here, delta R points this way. Now delta R is a vector, delta T is not a vector, okay? I mean, delta T is just a scalar, just a number. Delta T is just a number. So you can divide a vector by a number. We haven't talked about division. Okay, but that's what actually a scalar does. So what do I mean by that? Let's take a vector here, vector A. Now imagine you had another A and it's lined up like this. This is also A. Two A's put together. Okay, it looks like I'm adding them, right? So I start from the tail of the first A, and go to the tip of the second A, what I have here is A plus A. What is A plus A? It's 2 A's. So I can write 2A. Now in the expression 2A, A has the information about the direction, and 2 is just a number. But you're actually scaling A, you know? A was this, now you have twice the length. It's scaling it. That's why we call them scalars, right? Scalars. So this is nothing but multiplication by a scalar. Multiplication. It's not the multiplication of two vectors, it's still addition of two vectors, but what we end up with is actually a multiplication of a vector by a scalar, or with a scalar. So multiplication by a scalar. It scales it, okay? So I know that now 10A is 10 times longer than A, right? What if I multiply it by not a whole number? What about this? 0.5A. What is 0.5A? You know, I mean, you guessed it right. It's just half of the length. So 0.5A would be here. All right, so I don't need a separate rule for division. I just change my scalar that I'm multiplying it with. So that gives me, that corresponds to a division by 2, in other words. So this is equal to A over 2, right? So that's what is happening here. So in this expression for average velocity vector, I'm dividing my vector delta r, the displacement vector, by the scalar, which is delta t, and what I have is another vector. Now this vector has to point in the same direction as delta r. That's always the case. Whenever you have an equation, and your equation, which has left and right hand sides equal to each other, and those two, if one of them is a vector, the other one has to be a vector, and both vectors have to point in the same direction. All right? So delta r is right here. This means my average velocity vector, which I'm going to use red here, has to be pointing in the same direction. Now I don't want to clutter this too much, but I'm just going to draw a vector here. Okay, this is your V average. Now don't worry about the length of V average. Okay, it doesn't mean anything right now actually. Okay, please do not compare the two lengths. Delta r is a certain length. Corresponds to a physical distance between the initial and final points, but don't worry too much about the length of the red vector, which is the average velocity yet, because it's not comparable. Okay, it's like comparing apples and oranges, two physical quantities which have totally different, we call them dimension, unfortunately, not to be mixed with, confused with this 1, 2, or 3-dimensional business. But the dimensional quality of a physical quantity has to do with its nature. How do you derive it? Okay, so when you're comparing displacement with the velocity, please do not compare the lengths. I mean, I could draw this vector like really long, and that would still be correct. That's what it means. Okay. But the length of delta r, displacement, is something I cannot plane, I cannot change. That describes the physical distance. What about the length of the velocity vector then? Well, we're going to come to that. Okay, that tells you how fast you're moving, for instance. That depends on t, right? I mean, we don't know how much time passed here. If this happened in a very short time, that's going to give me a longer velocity vector, and if it happens over a long time interval, that will correspond to a short velocity, average velocity vector. But the important thing that you have to get from this is delta r and V are parallel. They point in the same direction. Okay, let me give you another example here. So let's pick an origin. This is point, the observation post, right? So here is my first vector, Ri. And here's the second vector, Rf. Now, do I know the path of the object moving? I may or I may not. Options. Okay, maybe this was the path of the bug, or the bug moved along a different path. Doesn't matter. I don't know. All I know is where the bug was at given time points, at t equals I, or ti, and tf. Okay, so the path, meaning whatever happens between those two time points, is irrelevant for my displacement and therefore the average velocity, right? So I'm going to take these 2 points and join them with an arrow. Remember, that's how I find Rf minus Ri. That is delta R. Rf minus Ri. This is my displacement vector, and the corresponding average velocity vector is along that direction. This is my V average, average velocity vector. Okay, now these are 2 different scenarios, scenario 1 and scenario 2. They look very different in terms of the paths, right? Doesn't matter if I know the beginning and the end points, initial and final, and if they are the same, I will get the same displacement and the same average velocity vectors. All right, so I'm going to write the definition again here. V average, a very important point. Delta R divided by delta T. So that is R final minus R initial divided by T final minus T initial. Okay, so this way I'm using vectors to denote both the position, therefore the displacement, and the velocity, average velocity vectors. Okay, so what else can I use vectors for? Now, in order to understand how these paths are different, I need more information. I need more information. Now, one thing is maybe Ti and Tf were seconds or minutes apart, right? A lot of time difference, a lot of time passed. What if I trace the motion of this object with smaller time intervals? You know, like instead of checking every 10 seconds, how about every second or every half a second? Or I have a high-speed camera, you know, maybe 60, 100 or 200 frames per second, you know, I can do that, right? Which means it's much easier now to tell the difference between different paths. It's 1 or 2, I know definitely now. So let's try to come up with a scenario where I have a, you know, a path like this, but instead of just focusing on 2 separate and far points like this, I want to find out what exactly happens in between. I'm going to just trace it with smaller time intervals. Now, if these are small enough, okay, if the time points I choose are really close together, then I know exactly what happens here. Okay, I can get really close to that shape. All right. So if I do that, what happens to the individual displacement vectors? Let's use blue. Now instead of calling this big vector here my displacement, since I'm going from here to there in a shorter time interval, now I'm going to have these as my displacement vectors, because each displacement vector here, the little blue arrows, is just the subtraction of this from that, or this from the other one, right? So I have these little arrows, and if they are short enough, they're gonna really converge to the actual path. Okay, actually smaller the time interval, closer to the actual path of the object. So each of these are delta r's. Let's call them delta r1, delta r2, and delta r3, and so on and so forth, right? 1, 2, 3. Therefore, I will end up with average velocities for each little segment, which will be parallel to the delta r's. Okay, the yellow arrows correspond to v average 1, v average 2, v average 3, so on and so forth. So by doing this, meaning looking at the motion within smaller and smaller time intervals, I will end up with a v, a vector average velocity, which is really becoming the instantaneous velocity. All right, so since the shape that I will obtain by adding these vectors, since the vectors are getting smaller and smaller, I'm getting really close to the actual path, the continuous path. The vector I end up with, meaning the velocity vector, will be the instantaneous velocity. All right, so at this instant, let's say, right here, when the object is right there, now all I have to do is this: draw a tangent to the path at that point, a tangent like this, and represent your instantaneous velocity vector as a vector along that line, like this. Okay? Again, the length doesn't really matter. I mean, it doesn't really tell you anything except for how fast you're moving, but I'm just going to pick an arbitrary length. But the direction is important, okay? Direction is along the tangent line, which means at a later time, let's say when you're here, the tangent points this way, so the instantaneous velocity vector points in that direction. Over here, right at this point, the instantaneous velocity, which I'm going to denote with just v without the index, right? This v is called the instantaneous velocity. Now, how this instantaneous velocity vector changes in time will give me what we call the acceleration. All right, so along this path, let's pick two v's, one here and one there. I'm going to call this vi and vf, and I'm going to call the difference delta v. Remember, Greek delta used for difference. Delta v is equal to v final minus v initial. I'm going to take this difference and divide it by the time interval again. So delta v divided by the time interval delta t, and I'm going to call this the average acceleration. Average acceleration, which is also a vector. All right, now let me start fresh here and show all these vectors. Okay, so here's my origin, with two position vectors Ri and Rf, and the actual path maybe looks like something like this, all right, which tells me that the velocity, instantaneous velocity, is like this at point I, which I call Vi, and the instantaneous velocity looks like this at point F, which I call Vf. All right, so the path already has a direction. That's the direction along the path. Now, what about the average velocity? We already know that. Maybe I shouldn't draw it, not to clutter this, but I'm just gonna show it here and then erase it. So we know that delta R is like this, right? Therefore, delta V is also in the same direction, all right? But I'm not worried about that right now. I'm worried about the average acceleration vector, all right? In what direction does it point at? Remember, that involves this vector, which is the difference, Vf minus Vi. I have to find where that vector is. Now, when I was finding Rf minus Ri, it was easy because both Ri and Rf start at the same point. So I just went from the tip of Ri to the tip of Rf and called it delta R. But now Vi and Vf are two vectors which don't share the same point. They don't originate at the same point. No problem, I move one of them. Okay, let's say I'm gonna move Vf. I'm gonna parallel transport Vf. So this is the direction of Vf, right? I'm gonna pick a line which is parallel to the first line right there. These two lines are parallel, and I'm gonna carry that, let's use blue, Vf, to where Vi is. So this is my Vf. Now both Vf and Vi start at the same point, and from now on it's really easy to locate where delta V is, right? So let's use blue. Okay, so you go from here to there. That's your delta V. All right? And since to find A average, all I have to do is to divide delta V by delta T. I will show A as a vector that points in the same direction as delta V. This is my average acceleration vector. Okay, so from position we obtained displacement. From displacement vector we obtained average velocity, and looking at the average velocity within shorter and shorter time intervals, we ended up with instantaneous velocity. And using the difference of the instantaneous velocities, now we have the average acceleration. These are just definitions, okay? And we're gonna go into detail, we're gonna find out how to work with these variables, but that's how these are defined. And if you take this business of looking at the object within shorter and shorter time intervals, which is also called limit process, can we find out an instantaneous vector for acceleration? The answer is yes. All right, so I'm not going to draw a picture for that, but just going to write it in the mathematical language. So V was the limit when delta t was so small, small meaning delta t goes to 0, right? So delta R, displacement, over delta t. This is nothing but the instantaneous velocity. In the same fashion, I'm going to define now instantaneous acceleration by taking the same limit, but now I'm looking at the average acceleration, which is delta v divided by delta t. Okay? And since if you've taken calculus, you know what these correspond to. And if you haven't taken calculus, it's okay. You can skip this part, but for those of you who know what I'm talking about, there's a different way to write this. You call it dr by dt. And this one will be dv by dt. And since v is dr by dt, right, the acceleration will become the second time derivative of the position. Right? Now, of course, in calculus, these were not vectors, and I'm going to talk about what the derivative really means in the case of vectors, but not for this part of the lecture. Let me mention one more thing. Now, velocity vector tells you how fast you're moving. An acceleration vector tells you about the change in the instantaneous velocity. Now, if you want to express this in terms of speeding up and slowing down, okay, what's the rule there? If that's what you're thinking, all you have to do is to look at the displacement vector and the velocity vector. So here's the rule. If the two vectors, displacement and the instantaneous velocity, if these two vectors are parallel, then you're speeding up. Okay, sorry, I meant the acceleration vector, sorry. You look at your acceleration vector and your velocity vector. The velocity vector tells you which way you're moving. If the acceleration vector points in the same direction, this means you're speeding up. If these two point in opposite directions, let's say your v is still this way because you didn't change your direction of motion, but you have now an acceleration vector which points in the opposite direction, this would mean you're slowing down. Okay, so for now, just remember these two rules, and this will relate the notion of velocity or the change of velocity to the idea of whether you're slowing down or speeding up. And of course, if you're maintaining your velocity, if you're not changing the direction and the length of the velocity vector remains the same along that direction, this means there's no acceleration, right? A is 0. So it's good if you just remember those two rules for now. If A and V point in the same direction, you're speeding up. And if A and V are pointing in opposite directions, you're slowing down. Like in one-dimensional motion. Let's say you're driving on the highway. I'm going to finish with this example. This is the direction you're moving, okay? So you have a definite V. It's definitely in this direction. Now, you may call this a positive V. If you want to, since it's one-dimensional motion, you can just work with positive and negatives, remember? So this means a positive velocity. If A is also positive, this means you're talking about the velocity vector, I'm sorry, an acceleration vector, which points in the same direction as V, then you're speeding up. Speed up. But if A is negative, this means you're slowing down. Let's make a table, and I'm going to finish with that. So if you don't have vectors, but if you just have numbers, okay, or values, let's say, for V and A, they could be both positive, like this one. They could be alternating, positive, negative, or negative, positive, or they could be both negative. Now, a negative velocity would mean you're moving to in the opposite direction, to the left. All right? So, if you're moving in the negative direction, V is negative, A is also negative. This means you're speeding up in the negative direction. If V is negative, but A is positive, you're moving in the negative direction, but left, meaning left, but you're slowing down because A is positive. Okay? So just keep this table in mind. So let's write here, these two that I circle means speeding up. And the other two are slowing down. So this is where I stop, and in the next lecture I'm going to talk about other operations you can do with vectors and other representations, which are called coordinate representations. And that will be the second part of vectors, and then we're going to find out formulas for how to find A and V and displacement. Okay, so I'm going to stop right here.